So you're going to be doing a lab over static equilibrium, and before you go in and start planning your lab and working on that in class, I want to just go a little bit briefly over equilibrium because that's the purpose of the static equilibrium lab. So the definition of equilibrium is a situation in which our net force is equal to 0. If you're in static equilibrium, that means that your velocity is actually equal to 0. So this situation that we looked at in our free body diagrams lesson was a box at rest on a ramp, and that was an example of static equilibrium. And in contrast, dynamic equilibrium involves a constant velocity that is non-zero, because if it was 0, then it'd be static. So you have both of these different cases here, one that's moving and one that's not moving. So this was our box pulled towards the right at a constant speed by the rope at an angle. Now, these problems are solved very similarly. And actually, even dynamics problems that are not in equilibrium where there is an acceleration is going to be solved through a very similar process. So let's take a look at how that process would be. Because if you're going to do a lab, you're going to be taking measurements of values that will allow you to find these forces in the different types of problems that you might solve. So your lab is designed to find measurements for the forces, set up equations with your net force equations, and then use those equations and your data to find missing values or to verify values. So in the static equilibrium example, we had the box on the ramp with gravity, friction, and normal force. Friction had to be present, otherwise gravity would cause the box to accelerate down the ramp. So just as a reminder of what we need to do to solve this problem, because we're on a ramp, we need to rotate our axes. So I'm going to define the positive x direction as up the ramp, the positive y direction as perpendicular to the ramp in the upwards direction. And then my gravitational force is at an angle, so I'm going to resolve it into components. So I'm going to have an FGX pointing down the ramp and an FGY pointing into the ramp. And then I'm going to put a squiggle here through my FG. Now, just as a reminder, my angle theta here that relates this triangle is the same as my 30-degree angle there. So once I've done that, I'm going to write my net force equation. So my net force equation in the x direction is going to be my positive values, which in this case is friction, minus my negative value, which is FGX. And those are the only two forces, so those are going to equal 0. And then in the y direction, I'm going to have my normal force in the positive y direction, and in the negative y direction I have FGY, and then those are equal to 0. So that's where we would have stopped on the free body diagram worksheet. So what you would do from here is then fill in some of the equations to set up kind of an information. So for example, I can sub in my definition of the force of gravity. So I can create this equation here where friction is equal to FGX, but then FGX would be the x component. So if I look at my triangle here, I want to find what that is in terms of my hypotenuse FG, because it's the opposite side I can use sine, so that's going to be FG sine theta. But I also know that my force of gravity is equal to mg, so I get mg sine theta. So what this tells me is if I don't know my friction force, I could find it if I knew my mass, my acceleration due to gravity, and the angle of the ramp. With the y direction over here, very similar process. I can see from this equation that my normal force is going to equal FGY. FGY is the adjacent side of this triangle, so it's going to be FG cosine theta. And then I can sub in mg cosine theta. So this tells me that my normal force is equal to mg cosine theta. And my normal force is one of those very variable forces that changes over time. So that way I can just use the mass and the angle of the ramp to get a decent value for what I expect my normal force to be. So that's kind of what you would do. So then what I basically now have is different equations, and we'll learn there's a relationship between friction and normal force. We'll learn that next week. In which case we could even further relate these two equations together because friction and normal force themselves are related. Now, if I wanted to then go over and look at this other problem, so my dynamic equilibrium problem, I can do the same thing. I don't have to rotate my axes, but my tension is at an angle to my x and y axes. I can set my positive x-axis to be the direction that I'm moving, positive y to be the upwards direction, and then I can write a net force equation in the x direction. But I notice, oh, my tension is at an angle, so I have to, it's not in x or y, so I have to resolve that. This was that same 30-degree angle, so I'll call that angle theta. You can't really see that. That angle is theta. There we go. And I can resolve that into components as well. Kind of a smaller angle, so it's harder to see. So I can make an x component and a y component. So this would be ftx, and that would be fty. So in the x direction, I would have ftx in the positive direction minus my friction force in the y direction, and that's going to equal 0 because I'm moving at a constant speed. There's no acceleration. In the y direction, I'm going to have my normal force and my y component of my tension minus my gravitational force, and that has to equal 0. So I can then write equations for these. So ftx has to equal friction in this case. Actually, I'm going to rewrite that in the other way direction so I can sub in for ftx. And then ftx is the adjacent side, so that's going to be ft cosine of my angle theta. And then that gives me a relationship between friction and tension. Now, a lot of times what happens is we don't actually know our tension, and we might not know our friction, so we could actually have a lot of unknowns. If I don't know friction and I don't know tension, then I have two unknowns. I might need two equations to solve. Well, that's where the second equation would come in, because I can see from here that my normal force plus my tension in the y direction, once again, I'm going to rewrite that. I'm going to rewrite Fg on the other side. That Fg is going to equal, I'm going to have to just rewrite this one so it doesn't matter, Fn plus Fty. Fg is mg. My normal force doesn't have an equation. And then my Fty would be my sine, because it's the opposite side, so that'd be Ft sine theta. So I now have two equations. I have this equation and I have this equation here. And once again, there is a relationship between friction and normal force that would allow me to tie those together, but I also have tension in both equations, which would allow me to tie the equations together. And then, so depending on what values I know, what values I can measure, which values I can't measure directly, I would be able to use these equations to solve for unknowns. So that is kind of the process that you use for setting up your diagrams, writing your net force equations, creating algebraic expressions for those that would then allow you to solve for missing values. Good luck on your lab tomorrow.